everybody. Please take your seats. We are going to start the session. Welcome to this session and workshop, mini workshop on kinetic reconnection. We are going to have 3 talks in the morning session, and then in the afternoon we are going to have 1 more talk and discussion. The first talk will be by Bill Daughton from Los Alamos on progress and future outlook of kinetic simulations of magnetic reconnection. So you have 40 minutes plus 20 minutes for questions.
Okay, sounds good. All right, I'd like to acknowledge my coworkers. Vadim Reuterstein is a postdoc at Los Alamos, has been working very closely with me. Brian Albright, Kevin Bowers, both at Los Alamos that played a central role in the code that I'm going to be using here in this research. Lin Yin is also at Los Alamos, a longtime collaborator. Homa Karamabadi and Kevin Quester at UCSD. Funding for this work is coming from the Department of Energy through the Los Alamos LDRD program and through NASA, the heliophysics theory program. And the computing that we've done for this project was on the Los Alamos Roadrunner machine and more recently on the NSF flagship computer Kraken. So reconnection, of course, has a wide range of applications that come to mind when people think about different areas of plasma physics. In magnetospheric physics, magnetic reconnection is thought to play a central role in the dynamics of the Earth's magnetosphere, both at the magnetopause and in the Earth's geomagnetic tail. In solar applications, pretty much all through the solar atmosphere, starting in the chromosphere, moving out to the transition region, and in the solar corona. Wide range of temperatures and densities, and thus collisionalities, where reconnection can play a role. In the last 4 to 5 years, there's been a lot of work about reconnection in the solar wind. Lots of interesting results of reconnection sites drifting by satellites and taking measurements in a way that would be hard in any other system. Of course, laboratory fusion machines, reconnection permeates that problem as well. And then a wide range of problems in astrophysical plasmas. I've just listed a few here. And it occurs in both hydrogen plasmas and in more exotic systems like electron-positron plasmas, which are usually highly relativistic. So when we consider these different problems that come up in reconnection physics, since this talk is on kinetic simulations, you may ask, well, when is a kinetic description really needed to talk about reconnection? When can you just fall back to a fluid description? And the thinking on that problem has evolved even in the last 2 or 3 years, when you really need a kinetic versus a fluid description. And this graph here kind of summarizes at least what I think is the current status in the community. And when we talk about this, we usually like to separate it in terms of 2-dimensional numbers. On the y-axis here, I have the Lundquist number, which is the magnetic Reynolds number. And on the bottom axis here, I have the system size in comparison to the ion gyre radius. And it's a double log scale here. Now, if in reconnection, if your diffusion region, if the resistive layers that develop remain bigger than an ion gyre radius, the thinking has long been that resistive MHD should be a reasonable description. And that's sort of what this solid line is going up to the dashed line. That if you fall into this blue region, no matter how you do the estimate, your resistive layers are going to fall below an ion gyre radius. It's very clear MHD breaks down, and you need a more complicated description. Even within resistive MHD, exactly what the scaling of reconnection is, surprisingly, is still an ongoing problem. That if you're at low Lundquist number, it's very clear from simulations and experiment that the solution is Sweet-Parker. Okay? The scaling for Sweet-Parker is very unfavorable, and that's been a motivation for a lot of work. But the fact of the matter is that you go into high Lundquist number regimes and it becomes highly dynamic, that these extended Sweet-Parker layers break up into secondary islands, and that there's been a lot of work from theory like Nuno Loureiros and simulations. Bhattacharjee group, Paul Kasich, many others have been looking at this problem in recent years. If a resistive layer breaks up into a chain of islands, you form new current layers between each island, and these layers are thinner than the layer you started with. So there's kind of a natural idea here that MHD will cascade to smaller scales. I don't want to go into too much detail here, but that's what this big yellow region here. It seems to be that there's a large region of parameter space where there's an unavoidable cascade down to kinetic scales, where kinetic reconnection can start to take over. Another line that is nice to put on this is the condition for the Dreiser limit. When does your reconnection electric fields exceed the runaway limit? And also that you can see there's a big region here of parameter space where it's going to exceed the runaway limit. You cannot have ordinary resistivity work anymore, and you need some kind of kinetic dissipation process. So if you start putting problems on this double log scale, laboratory reconnection experiments sit down in here, kind of right on the border of this transition between kinetic and collisional, and also right on the border of where you're going to hit runaway fields. The Earth's magnetosphere, can we turn the lights down just a little bit? So some of these will show up better, some of the movies. The Earth's magnetosphere is firmly in a collisionless regime, no matter how you do the estimates, that collisions can never really matter. But if you start looking at different regions of the solar atmosphere, you can see that you're in this regime here where plasmoids are thought to play a crucial role, and it's not so clear exactly whether you can do it with collisional MHD or kinetic. I mean, the recent results seem to implicate that it's going to be a kinetic problem. Okay. So let me discuss then briefly kinetic particle and cell simulations, so that our approach to this problem. That if you work with the full plasma kinetic equation, it's essentially a first principles description of reconnection then for all parameter regimes, going all the way from collisional MHD back to the collisionless Vlasov limit. And so particle and cell techniques are very well developed. The approach we're using is in this VPIC code that was Kevin Bowers at Los Alamos was the primary architect for this around the kind of 2004 timeframe. It's relativistic full Maxwell treatment. That within the code we have a Monte Carlo treatment of Coulomb collisions using this Takazuke-Abe particle pairing method. So that you can, within a cell which is on the order of a debye length in these PIC simulations, that you can randomly pair up particles and periodically let them undergo a binary collision in velocity space. If you do this in the right way, you mimic a full Fokker-Planck operator. And then we've carefully optimized VPIC to exploit the newest petascale computers that are coming online in the last few years. Okay, so in principle you get, yes?
Is this way of colliding them, does it mean that everybody effectively collides with everybody within a cell, but not outside, or does it actually depend on how far they are?
No, you're only pairing them up within a cell. The cell is a debye length in these calculations. Beyond a few debye lengths, you're exponentially screened, right? So physically, those particles would never see each other anyway in a real plasma, right? And right, so that you create random lists, you pair them, and you do a velocity space scattering operation on them.
Yeah. And that's done in some, that you put in some white noise on them that reproduces the right collision frequency or something, or do you actually do another port collision?
No. You're sampling from a distribution that will mimic Coulomb's screened Coulomb cross-section in velocity space.
And the equation solving is the Vlasov equation rather than the Gyrokinetic equation.
That is right, yeah.
And it's full F rather than delta F.
That's right. Mostly what we've done is full. Everything I'm going to show here is full F. So the difficulty with doing this is it's really just brute force. You need to resolve all your kinetic scales for both your ions and your electrons, and all your time scales as well. And what we really care about to get most reconnection problems is to be able to push out to the macroscopic scales, the macroscopic spatial scales and the macroscopic time scale, which really for us is the global Alfvén time. In order to say anything interesting about it, you really want to be pushing in this range, but you're using a lot of your computing power really to resolve your microscopic physics, and particularly this separation between ion and electron kinetic scales. So for spatial scales, that's a square root of a mass ratio, which is not too bad with today's computers. But the time scale, it's a mass ratio separation, and it really is very, very difficult. So often in these types of calculations, we're treating mi over me as a free artificial parameter, and using reduced values in the range of 100 to 400, and trying to make scaling arguments on how it goes back to hydrogen. Now with petascale computing, if you limit yourself to two-dimensional problems, there's a wide range of problems now you can just do for hydrogen mass ratio and check if your scaling predictions are true. But if you do that, then you cannot push as far towards your macroscopic scales because you spend all your computing on that. Okay? In 3D, even with petascales, you cannot really do a hydrogen plasma. So it's crucial then to have a theoretical understanding of what you're looking at, and to be able to extrapolate that understanding to real systems. Okay, so petascale machines that have been coming online in the last few years offer a lot of opportunities to push these kinds of problems to bigger systems, but there's also some real challenges in order to run on these machines. You cannot just take a code that was designed for the previous era and necessarily get it running well on these machines. The first one we got going in order to move along this path is the Roadrunner machine at Los Alamos, which is built around these cell power band broad engines. They're the same type of chip that's in a Sony PlayStation, and they have 9 computational cores. Kraken and Jaguar are based on AMD processors, and they have 6 computational cores on each chip. So this is the general trend of computing, is the individual computational cores pretty much aren't getting any faster. In order to maintain the exponential increase in computing power, you have to throw more and more computational cores at it. And then that can be a real programming challenge. So for Roadrunner, we had about 110,000 cores, Kraken about 100,000, which we've run on, and Jaguar is up to 220,000 cores. If you can get a code to run on this, though, it really is permitting an exponential increase in the kind of problem sizes that you can work with fully kinetic simulations. So this is billions of particles within the simulation as a function of time for full PIC simulations, at least that I'm aware of. The fastest ones back in around 2002 were the Livermore codes, around 8 billion particles or so. This is kind of the era where the VPIC code was first developed. My own PIC calculations, I have my own parallel PIC code that typically only scales to about 500 cores. And these are kind of the problem sizes that I was considering before I became involved with the VPIC effort, a few billion particles. I came back to Los Alamos in 2007 when they were kind of ramping this effort up. And right now on Kraken, we're above 1 trillion particles for a number of these runs, about 1.3 trillion particles. On Jaguar later this year, we hope to scale that up by about another factor of 2 to 3. Blue Waters, if that works as it's expected, you could easily do over 10 to 20 trillion.
Where is that? I don't know that.
It doesn't exist yet. They had proposals for it, and we put in a proposal.
They told them to deny existence of that computer.
No. This is the Los Alamos one. It's sort of behind the fence now, and it's hard to use. But Kraken's the flagship NSF machine that anybody can write time on that one. Jaguar is the flagship DOE Office of Science computer.
I have a kind of tangent. How much does it cost to develop something like Jaguar?
To do what?
To develop it, to build it, and run it. How much does it cost? 100 million?
For a computer like this?
Yeah.
Oh, $100 million, a few $100 million or so.
So it's like a SMAX.
A SMAX?
It's like a small
scale space mission.
Yes, but then computing is used across wide areas of physics and chemistry, and it's expensive. The electricity alone that these machines are burning is megawatts, 4 to 5 megawatts. So you can $500 an hour in electricity.
Well, if you launched it into space, you could put solar panels on.
But actually that brings up this problem that maybe this exponential growth will have to stop simply because we'll run out of money to buy these machines.
You cannot keep scaling up what they're doing. You'll need a nuclear power plant to power the computer. So power is the...
Apart from the power, just the cost of the fusion works.
But that's not obvious.
It's not obvious.
That's
No,
what the
because
rest
I
of the
think
workshop is about.
The earlier computers were still very, very expensive, so I think certainly the price per processor must have gone way down. Way down.
Way down.
But is it true to go down?
Yeah, I'm sure it must.
Yeah, iPhones are cheaper every year. No, it's the same cost curve.
Look,
I thought Roadrunner with these new PlayStation chips, that must have been cheaper, right? I thought.
it's cheaper and it uses a lot less electricity. That we could not, at Los Alamos, we do not have the electricity alone to build a Kraken type machine.
So why didn't they, and for Kraken and Jaguar, why didn't they stick with the PlayStation type chips?
Because they're harder to program. They're much harder to program and get the good performance on. Yeah. Whereas, so it's a bigger switch. You're using 3 types of processors really on Roadrunner.
Yeah.
Where
communication is the issue, right?
What?
The GPUs, communication is
Communication could be, yeah. On Roadrunner, we ran entirely on the cells. We didn't use the AMD. But anyway, what I really want to talk about is physics, though. It's, yeah.
was making a good point. Are we a spin-off of the computer industry then? Computer gaming, computer
Oh, well, video games are driving computing. I mean, there's no doubt about that.
When do you have more?
Video games or porn?
When do you have more power simulation than nature has?
Well, we don't have to worry about that. You look in the magnetosphere, right? That the collisionality parameter, the number of particles in a Debye sphere, just 1 Debye length. That's like 10 to the 10th, 10 to the 12th, right? So I mean, and that a Debye length in the magnetosphere is just a pinpoint. I mean, you can never have as many particles as nature. But and thankfully, with the particle and cell technique, you don't need as many particles as nature to capture the essential plasma physics. Okay. So using this is about a factor of 100 to 1,000, where the kind of simulations I could do 4 years ago. And so we're looking at a range of 3D problems that primarily involve the stability of elongated current sheets. I'm going to get into this more. The types of kinetic instabilities that can occur in elongated current sheets. We're doing it for boundary conditions relevant to the MRX experiment. We're doing it for collisionless open boundary systems that are relevant for space, using both neutral sheet geometry and in guide field geometry. It turns out that the physics of 3D reconnection in guide field geometry is very rich and complicated. And that's what I want to focus mainly on in this talk, so not to make it just show and tell here. So, but to motivate this, I want to give you like 4 slides showing that extended current sheets and secondary instabilities, secondary reconnection instabilities within these extended sheets, that these seem to be a common feature of reconnection in large-scale systems, all the way from electron-positron plasmas up to hydrogen plasmas, both for strong guide field reconnection, all the way back to neutral sheet limit, and also for both collisional regimes, going all the way back to collisionless regimes. This seems to be true at this point. Okay, and that this is one of the major motivations for going to 3D, that it's been known for a long time that thin sheets that reach sort of the ion kinetic scale, those are the preferred sites for the onset of reconnection. You start getting, at that point, the collisionless tearing instabilities can be very fast and trigger an onset of reconnection, but also other modes. But reconnection itself, as it gets going and it develops, it non-linearly makes new current sheets. These new current sheets in the collisionless regime are on electron scales and thickness that can extend much beyond the ion scale for their total length. Okay? And because of that, these highly elongated electron sheets can be unstable to secondary reconnection instabilities, sometimes called secondary islands, sometimes called plasmoids. So this is a neutral sheet limit on the left. This is the limit of a strong guide field on the right. And so these may play an important part on many aspects that we care about reconnection: the rate, the energy partition, particle acceleration, and other problems. that using VPIC on Kraken, we've recently verified this basic scenario all the way up to a hydrogen plasma. This is one that took us about 3 to 4 days to run on Kraken. Here's the ion outflow jets, and then we've sort of zoomed in on this electron diffusion region. This is the out-of-plane current sheet. You can see a secondary island that's starting to shoot out. This particular one repeats it over and over again, about 5 times. This is the electron outflow. These electron outflow jets tend to be even more elongated than the out-of-plane current sheet.
So where's the ion layer here?
The ion layer is, it's the whole region essentially. So this is the ion outflow jets,
Oh, I see.
right?
Is that the whole box? Oh, it's open.
No, it's open, but it's not even close to the whole box. I'm still zooming in on it.
And there's no guide.
There's no what?
Guide.
This case is a neutral sheet, that's right. So in 2D, using these types of simulations, you really can go all the way up to hydrogen plasmas and then test scaling predictions now, which is really helpful, I think. Here's another example. This is using turning on the collision operator within VPIC to explore the influence of these secondary islands within collisional regimes. So in this simulation, it's 800 ion inertial links long, and we're starting in a regime where it really is collisional, that the kinetic effects are really not playing a role in this top panel here. The reconnection electric field is nearly entirely balanced by ordinary resistivity, the Coulomb collisions in the problem. As this simulation develops, you get a chain of plasmoids that grow. This is what this theory that Nuno Loureiro developed. In between each of these plasmoids, you get a new current sheet. Those new current sheets are at a thinner scale than the original overall resistive layer. If the new current sheets hit ion kinetic scales, that's the point where we see an abrupt increase in the reconnection rate. And that at that point, you can easily go above the runaway limit. And the new current sheets that form beyond that point go all the way down to electron scales, is what we conclude. And in these weakly collisional electron layers, if you zoom in on them, there's also appear to be unstable to the formation of new islands. So you have islands over a wide range of scales that appear to grow up. So here's a movie showing the evolution of these islands for an electron-positron plasma, where we can use our computational power then, instead of resolving the scale separation between ions and electrons, instead use that to push it to a larger system. This is a large open boundary system, where you can see these islands just forming over and over again. It never settles down to a steady state. And the reconnection rate oscillates in time as you form these islands. So it's trying to reinforce my point that these seem to be a general feature of large systems. But there's real questions. How do you extend these results to the real 3D world? That in the real 3D world up there in space, you never have nice symmetries of a laboratory machine. So the whole concept of what do you even mean by a secondary island? You probably never have really well-defined flux surfaces. In 3D, I would say in general that magnetic islands really correspond to extended flux ropes, although the language of how we discuss this in 3D hasn't settled yet. So often people just use islands to mean in space these extended flux rope structures. As I'm going to discuss in this talk, there's considerably more freedom to form these islands in 3D. That's one key point of this talk. That another key point is these islands or these flux ropes can interact in a variety of complex ways that is not possible in 2D. I think normally this gives rise to the formation of stochastic magnetic fields, and this may have a potential influence on every aspect of the problem. So here in the bottom I have in red that there's a real need for theory on this problem, both to describe the primary islands that form within these sheets, that's what I'm going to talk about, but also the secondary islands, these secondary instabilities. And so the rest of this talk I'm going to focus in detail on one problem, just the island formation problem in guide field geometry. The theory, of course, we can do it at any mass ratio. But in order to really attack this problem in 3D, even with petascale computers, you have to use a pretty reduced mass ratio. That's one of the points why theory is so important to understand what you're looking at. Okay, so island formation, people have known for a long time that it's more complicated in 3D. In kinetic regimes, a lot of the work that I'm going to talk about relates back to drift tearing modes, which have been studied for a long time in tokamak plasmas and other fusion plasmas. The work that I'm going to talk about is most relevant, actually the same problem that Galeev and collaborators wrote a whole series of papers on. But there's some real issue just with the linear theory in this work, that a number of the things just simply aren't right. And I'm going to tell you the way we see this problem. This is Galeev's picture of what he thinks it should look like from the linear theory. And I think partially based on this type of picture that Jim Drake has been looking at these problems to try to understand, if you did get all this island complexity, what implications would it have for the particle acceleration problem? But not exactly where did the islands come from in the first place. So I'm not looking at particle acceleration here. I'm more asking, can we go beyond a cartoon picture and say, well, can you really get this in nature? So to do that, the simulations I'm going to show are all within Harris sheet geometry with a guide field. So across the layers, the z direction. Here's the reversal that's driven by this current that's into the plane. And then we impose upon this a uniform guide field. Okay, so I just want to say a few things about the linear theory of tearing modes. That everybody knows that tearing modes are localized about the singular layer in a plasma where the parallel part of the perturbation goes to 0. That a tearing perturbation in general has an inductive piece that drives it, and an electrostatic piece that tends to want to short out that low frequency perturbation everywhere except in the special regions where the parallel part of the perturbation, the parallel part of the wavelength is going to 0. Okay? When people do 2D simulations of reconnection, they're usually doing it in the ZX plane, and that only allows the singular layer to be right in the center of the plasma. Okay? But you can see in 3D, if you allow a finite component of the wave vector in the out-of-plane direction, that really tearing modes can exist at any location in the current sheet that's consistent with your overall boundary conditions. And so for a Harris sheet geometry, we can just write down k dot b equal to 0. And for a given guide field and a given wave vector, we can say where the singular surface would be for that perturbation. So for like this picture, this cartoon that Jim Drake has been drawing, that if you look at one of these islands that are somewhere near the center, that would be a traditional tearing mode where your singular surface is near the center. But any of these that are off-center have to be oblique modes where they have a finite component of their wave vector in the out-of-plane direction. So those can only really occur in 3D. In hydrogen plasmas, that this mode for the oblique modes pick up a real frequency on the order of the electron drift frequency. So they really are drift tearing modes. If you go to the pair plasma limit, because of the symmetry there, the mode is always purely growing. You don't ever pick up a real frequency. So there's some fundamental differences between those two limits. Oops. Okay, I think I'm missing a slide here. We're looking at the linear theory of this problem from two different ways. And the slide that I'm missing describes a formally exact way of doing the problem, where you don't do any asymptotics. You basically solve the linearized Vlasov-Maxwell system directly using a finite element approach, including all kinetic effects, and assuming your full perturbation. So you have all three components of your vector potential and your electrostatic potential. So it's a formally exact way of computing these modes in thin sheets. That's what we have on one hand to check what these should be. And as we've used this over the years, it's extremely predictive. It tells you exactly what you're going to see when you do the kinetic simulation. But it's using this technique, it's hard then to understand the physics and the overall trends. And that's one of the key things that you're really interested in, is to be able to quickly understand the parametric dependencies in the problem and what physics is setting that. So in the last 6 months, we've tried to go back to the traditional asymptotic approaches to look at the tearing instability. And we've developed a new theory for this. And as I mentioned already, I think that there's some really serious issues with the previous body of work on this. Surprisingly, starting with what the outer layer equation is. Normally, you don't even think about this in tearing theory, that the outer layer is essentially an MHD response, and that Firth and Rosenbluth's classic work on this problem, that it's very well laid out what the outer layer equation is. The people that did a kinetic analysis, though, tried to do it just from the kinetic equation. And their outer layer equation in the limit where you don't have oblique modes is correct. But as you go to the oblique modes, they're missing an important term. And what this means is that the delta prime that was used in the previous work, we also believe is incorrect. And the third issue is the asymptotic matching is trickier. You cannot do it in the same way for the oblique modes as before. You simply you do not recover the answers that we see when we solve it with an exact Vlasov solution to the problem. So in the brief time I have, I don't have time to discuss the linear theory really here. I just want to quickly throw up our analytic result. The delta prime, our approximate delta prime that we come up from the problem is of this form. This is the classic Harris piece that has a nice analytic solution to it. The rest of it is a functional form that satisfies some nice limits, and we can show numerically that it's right to within a few percent. The important thing to bring away from it is this term. This is hyperbolic tangent. This is your location of your singular layer. And what this means is that your delta prime is increasing as that singular layer moves away. So this term will tend to drive your mode to oblique angles, always based on just delta prime. Now, that delta prime alone doesn't give you your growth rate. You have to do your matching with the inner layer. And there's a variety of dependencies there as well that can counteract this. Yes?
Do you mind if I interrupt you? Oblique modes means that they have both kx and ky.
Yes.
And here there is only one k.
There's the magnitude of k, and then there's a zs. Zs is the location of your singular layer where k dot b is 0. So that's where you can write that in terms of theta or ky or anything.
So there are two parameters describing the mode.
That's right.
Choosing kx, ky, choose k, the magnitude, and...
Exactly. I can rewrite it in terms of angle if you want.
I think Yeeman Wang also found this peaking off the axis. I don't know if you've seen his paper.
No, I'd like to see that.
You might want to look it up. I mean, it's the MHD limit, but he also found...
Did he do it with a theory?
Yeah.
Oh, good. Yeah. I would like to see what his delta prime is. Because this is the same delta prime, if we've done it right, that you should use in MHD theory. Okay. I'm running way behind here, but basically with an analytic prediction, then we can say what range of guide fields that should tend to drive the modes oblique. And basically for the long wavelength limit, if you have a guide field comparable to your reconnecting component, that's the limit where it should drive it oblique. So here's some example comparisons between the exact Vlasov solution and this simple theory. This is for the limit of an electron-positron plasma. There's 4 different sheet thicknesses here, from rho I over L of 0.1 up to 1, right? So over this parameter regime, the growth rate is changing by a factor of 1,000. But you're getting it to within a factor of 2 here with the simple theory, and you're getting the right range of angles. The range of angles here is from 0 to 45 degrees. So let me now go back into some simulations and show you what this all means. This simulation is for the 2D limit of a paraplasma, where then you only allow a single resonance surface to occur in the system, and it's right in the center of the sheet. So you can see as islands develop, new sheets form, secondary islands continuously come out of that.
What do you do with the boundaries?
The boundary conditions for this set is periodic on this boundary, and they're conducting boundaries up and down.
Oh, so that's all one layer.
It's all one layer. Okay, now let me show you the difference between 2D. This is about 1 million cells. This is a slice through 3D. So that's 1 billion cells on the order of it. They're the exact same simulation parameters, and they're synchronized in time here. You're watching the same time evolution between these two.
How long
Oh, these are very quick on paraplasmas. Even in 3D, you know, I don't know, 4 or 5 hours or something probably for
No,
those.
I meant like.
Oh, these in terms of T omega CI, some of these will be like 5 to 800 or something. Okay, so clearly oblique modes are totally changing the solutions between these two. And if you, actually let me just skip this since I can come back to that. And
Bill, is it oblique tearing modes or is it this drift kink type of thing?
no, these are, well, let me go back then. We would claim these are all oblique tearing modes. And to visualize that these are an isosurface of the, people see this? These are isosurfaces of density. So you really are visualizing these oblique islands to start with. On the top, there's a set of islands in one oblique direction. On the bottom, they're in the other oblique direction. And it's almost plus or minus 45 degrees. So it's a full range of 90 degrees where these oblique islands can grow up. And what the movie just showed there is I'm melting away the isosurfaces. So you're looking towards the center of the sheet and seeing all these oblique structures, which all of them are consistent then with what I was showing on the theory there.
So does the guide field stabilize the drift kink mode?
There's no, yeah, that's right. For this range of guide field, there's no drift kink mode. You want me to run it again? I'm almost out of time.
He's in charge, so as long as you're understanding.
I mean, it's you can.
We have
Okay.
There is
Okay.
discussion, so.
The coloring here is current density. The isosurfaces are particle density. So the surfaces are looking at the structure of your ropes. The color is showing the magnitude of the current density. So as you melt it away, you're seeing more red. Those are higher current density. And then there's a whole framework of these structures. The magnetic field is very complicated as it threads through this.
John, is this overall, why is this all diagonal? I mean, what is the angle?
Yeah, if I don't get this, that.
Special about the diagonal direction?
The parameters for this simulation are somewhere actually in between these two. Okay? These curves predict the growth rate of these oblique tearing modes as a function of angle. So the prediction is that you're going to get almost the same growth rate, or perhaps even a little bit faster growth rate here at these oblique angles as you do for this mode, which is what everyone else studied. Okay? This simulation then allows the whole spectrum of modes to grow up.
Right. But that was already fully nonlinear. Right?
Very quickly, it's nonlinear here. But you know, okay, let me. So then if you put it all together, this is the 3D evolution. So you're looking at current density along these planes. Those are the normal 2D slices. And this is the development of this structure as a function of time. So again, on the top surface, they're almost plus 45 degrees in one direction. The bottom, like minus 45 degrees. But then there's a continuous production of new flux ropes coming out of these thin current sheets. That's beyond our theory, way beyond. And then I think that would be really neat to see some theory on that. Okay, so here's a run we did on Kraken just a few months ago where we scaled this up even further. So 3.3 billion cells, 1.3 trillion particles. And again, you see this same type of complex evolution that's beginning to look highly turbulent. I'm going to show you a 3D rotation of it again, but like here's one of these reconnecting current sheets. Each one of these blobs you see here corresponds to one of these oblique flux ropes. And each time you see a spike in the current density here, that corresponds to a new flux rope that's being produced within this layer.
How big is the guide field?
This is a guide field of 1. We think that the guide fields of around 1 is when it's going to reach its maximum complexity in terms of this oblique structure.
But you have explored other values.
What?
You have explored other values, have you?
We have. We've gone up to guide fields of 1.5 to 2 and down to guide fields of 0.5. So there's some range of guide fields here. Okay, so what implications are of all of this? Well, we're only beginning to understand. But if you look at just one thing, the global energy conservations, these three examples were all periodic, so it's very easy to keep track of where the global energy budget is going. So on this y-axis, I have the fractional decrease in magnetic energy as a function of time. And the black curve is the corresponding 2D run. The blue one is the 3D run done on Roadrunner. The red one is the even larger 3D run done on Kraken. So it's clear that the rate of the energy conversion that's going on here is slowing down considerably. It's a factor of 3 times slower on this largest run than on the 2D limit. If you just scale the 2D problem, we can scale that a long ways. It does not slow down. That the formation of new islands seems to solve any Sweet-Parker problem you might expect. And the rates oscillate wildly in time, but it doesn't slow down. 3D, it doesn't seem to be a subtle effect. It is slowing down. And why would that be? Well, intuitively, in 2D, the extended current sheets that form can just always be broken up by these islands. So you have a nice coherent inflows, nice coherent outflows. In 3D, all these oblique structures, they tend to compete with each other, is what it looks like, and destroy the nice coherent process that you're developing. So, in 2D, a lot of our work was trying to promote the idea that secondary islands might be part of the solution to scaling up reconnection. Surprisingly, this seems to point in another direction, that if you get too much of this complexity, maybe it would push it in the other direction. So that you never know where research is going to take you. So the important question you guys probably care about is, does this work the same way for hydrogen plasmas? I'm way out of time here, but for hydrogen plasmas, to do the linear theory and to get it to agree with the Vlasov code, the matching is trickier. If you take a delta prime where it's defined all the way, taking epsilon equal to 0 in your outer region equation, you get curves like this, the red curves. That does not capture the trend that we see in the full Vlasov curves. These are growth rate as a function of the angle. Okay? So the simple theory would say you would drive it over a broad range of angles. The more precise Vlasov approach says no, it's only about 10 to 15 degrees. If instead we do the asymptotic matching where we compute a delta prime on the edge of the ion singular layer, that you actually then start to recover the trends. And then let me just leave it at that. And if people want to discuss it in more detail, why I think that's the right way to do it, we can do it afterwards. Okay, simulations confirm this. You do not, if you go to higher mass ratio, we can of course do hydrogen with a simulation, but we can do the theory. And there's not big changes in the theory from mass ratios of say 60 to the 100 beyond of upward. That the prediction is that you have a much smaller range of angles. So this is one at a mass ratio of 64, and these are the types of ropes that are growing up. Some kind of a modest range of angles of around 10 to 15 degrees. But the ropes, as soon as they begin to form, they do interact in very complex ways that you cannot describe by 2D models.
All the yellow lines.
There are just a few magnetic field lines. We don't really know how to visualize the magnetic structures here very well yet. So there's just a few sample field lines. So I would claim that the linear dynamics of these layers does not give you really this picture that Galeev was promoting. But what about secondary instabilities? Could secondary instability still give you a similar picture? And the important point here is that even in 2D, the work of Jim Drake and myself and others have shown that these extended current layers will form these secondary islands. At least in our simulations, we tend to see these secondary islands very near the original X line, where the current is primarily in this out-of-plane direction, and then the fastest growing Terry mode will have a K vector in plane. But out here along the separatrices, where you get these highly extended layers, the current is rotated to have a strong in-plane component, which means the fastest growing Terry mode needs to have a finite Ky, and you would only expect it to see it in 3D. So our conclusion is that these layers here in 3D can also be unstable, structurally unstable to these secondary modes. So here's a 3D evolution trying to show this from Roadrunner. This is the normal reconnection plane that you would be looking at. The big ropes here are your primary islands. They're somewhat oblique, but not strongly oblique. The important point is that separatrix current sheet breaks up into a highly filamented structure at all sorts of oblique angles as a function of time. And we claim that these are also oblique flux ropes if you plot a few magnetic field lines on it. That if you go ahead and do a cut across one of these separatrix current layers and look at the profiles of the current and the magnetic field across one of them, that you can see that these thin current layers, which are on the order of a few skin depths thick, still have very intense magnetic shear across them. This particular example has a rotation in the magnetic field of around 40 degrees across on a layer that's only a few electron skin depths thick. There's no reason to believe that's structurally stable in 3D. And if you look at the angle of the flux rope that tends to form at this location, it is consistent with the idea that it's a secondary tearing type instability. Okay? But there may be other possibilities too. And here I just do a rotation of this out of plane and throw on a few magnetic field lines in this region. And you can see how these current filaments are strong enough such that they lead to a wrapping of the magnetic field lines around these current filaments. Okay, I think I go to my conclusion slides now, and then we'll still have some time left for open discussion. So, summary and a future outlook. These petascale computing is allowing kinetic simulation studies of reconnection 100 to 1,000 times larger than was previously considered state-of-the-art. And I think there's a real potential for breakthrough progress in reconnection physics if we can effectively use this tool. I'd like to emphasize, though, that computing should never be a substitute for thinking, that there's a real desperate need for theory on this, for laboratory experiments, for space observations, all sorts of exciting space missions on the horizon with new, exciting results from Themis, and there's a new mission, MMS, that directly focused on the physics of reconnection. However, computing can let you move beyond cartoons and challenge and explore new ideas in a way that is extremely powerful. It's undeniable. Okay? We've put forward a new asymptotic theory that offers some simple predictions of when you would expect to see this kind of complex evolution versus the more quasi-2D picture. And I think that's powerful. For guide field regimes, it appears that if you go into this regime where this happens, that the dynamics is inherently three-dimensional, and this could have far-reaching implications for lots of different things. I've already talked about the dissipation rate, the generation of stochastic magnetic fields. If you do Poincare maps in systems of this with double periodic boundary conditions, as soon as you see this start happening, it destroys flux surfaces. People have known this for a long time, of course, in tokamaks. Okay? It's not clear, though, for large open systems in space, how will we exactly map the structure of the magnetic field. Here's a primary conclusion. I think studies of reconnection in large 3D systems will be increasingly interconnected with research in turbulence as we head in towards the future. Turbulence that's self-generated within the layers themselves, but also pre-existing turbulence that's connected in from the upstream direction due to kinetic instabilities, MHD, waves, all sorts of things. That all the studies so far, these kinetic studies, just have a laminar plasma convecting in. It's not hard to imagine that if you had turbulence convecting in, perhaps it may even seed more of these types of flux ropes. And then if they do impact the dynamics, you would need to somehow understand that. And then as a final thing, I would say even in 2D, there's lots of unsolved problems. There's lots of problems we would like to do that were beyond the reach before. But with this extra factor of increase in computing power, you can start considering problems in 2D that were intractable before. Here's a a 2D particle and cell simulation, fully kinetic, of a flow interacting with a dipole. Okay? We can't do the same dimensionless parameters as our Earth, but we can do parameters that were similar to what hybrid simulations were doing about 8 or 9 years ago. And so there's all sorts of different problems you can set up now that before were intractable. So let's end it there.
We still have a few minutes for questions.
I have a question about I like the off-axis or off-current sheet island. I saw in the data, or published from data, where we saw a secondary island produced in reconnection, and it was not on the main field reversal, but away from the axis, away from there, and it confused me.
That would be interesting to hear more about that. Because that's one of the key predictions from this, is that if you see an island, it does not have to be in the center of your outflow.
Right, but the guide field was essentially zero.
Oh,
So
then I have no idea.
I wonder if you wrote it, showed a guide field one, but if you have if you approach the limit of zero guide field, you have done a simulation of that.
The limit of zero guide field, we've done some of those, but not in the large systems. Those we were focused on drift wave instabilities, which I'm going to talk about some on Thursday for this MRX stuff, where you really need to go to very high mass ratio in order to properly capture the physics of these lower hybrid drift turbulence that's in there. But
Maybe
to do these...
Maybe the Hall field is large enough to produce something that's similar to a guide field.
Maybe. In other words, I wouldn't necessarily rule out that the separatrices are structurally stable even at zero guide field. But we haven't done the simulations to test that. I would say any 2D result where you see an extended current sheet, you should worry about whether it's going to be structurally stable in 3D.
More questions?
Go ahead, Peter.
Thank you, Bill. You made a comment that some theory would be helpful, but you're using a full 6 dimensions in time simulation. Are there any reduced descriptions that pick up any of the physics properly?
Like gyrokinetics.
Drift kinetics, gyrokinetics. I mean, I assume fluid descriptions work in collisional plasmas to some extent.
Well, it's ongoing work. That the most pronounced difference we don't understand right now between two fluid descriptions and these fully kinetic is that the two fluid also develops multiple scales, current sheets. They have electron scale sheets, but they tend to be much shorter than in the fully kinetic. No one understands why. It seems like the closure that's being used in two fluid models, which is missing things.
Yeah, how do you get a closure for a two-fluid model? You don't know how to do
Well,
that.
Jan has some ideas. I don't know if he's going to talk about it.
Plasma, that's tough.
Yeah, another problem that I'm working on is trying to compare the fully kinetic simulations and theory with reduced models like gyrokinetic. This Yu Lin at Auburn is working with Lu Chen, and they've put together a model where the ions are fully kinetic, like I'm doing, but that the electrons are gyrokinetic. And so we're trying to do detailed benchmarks between that model for in full Pick and full Vlasov theory for the problem of the lower hybrid drift instabilities that can be triggered in these layers. And right now there's some similarities and differences. Yeah. But I think the theory can be useful from all sorts of different directions. It doesn't have to be full Vlasov in order to have insight to certain aspects of these questions.
So my question is along similar lines. How would you expect things to look at a guide field without?
Well, let me see if,
Oh, good, in the picture.
well, just one important point I wanted to make. I have the right slide here. Look, yeah, I can't find it. The range of angles that this can occur is limited by the need to fit your singular layer within your current sheet. As you go to the limit of very, very strong guide fields, then that range of angle is being squished down again. And so you cannot get these highly oblique modes just because of that consideration. So that's one of the things that leads us to believe that guide fields that are around unity is when you're going to see the maximum complexity in terms of these oblique modes.
Right, but that's
For
the
current
hardest thing
sheets.
to study.
It is, but it's, you know, like for magnetospheric dynamics, it's the relevant thing to
So you
study.
have a prediction, like in solar wind reconnection, the most islands should be seen around the plasma region, or guide field.
Well, the broadest range of angles. Yeah.
That's what you want.
Yeah, as far as getting these secondary islands in general, I don't know. Like I think in Jim's simulations that you guys see more islands with a strong guide field, right?
Yes, well, yes, we do.
Yeah.
But those are secondary islands.
Right.
That's a different statement than the oblique modes.
Right. But also then the issue of the, yeah, I mean, there's the primary islands and the theory for that, which I think we have a pretty good grasp on. But then the issue of the secondary islands, no one has a good theory for. And so it depends on what kind of current sheets develop for a guide field of 1,000. I don't know what they should be. And then the orientation of the current within those layers in comparison to your initial geometry. That if somehow you orient the current at very different angles and form an extended layer, then I don't know, yeah, I mean.
Hey, can I ask one question about the comment you made about asymptotic matching? Is the key question where you do the matching, or is it the oblique nature of the modes that's causing this difference? You're matching, you said.
It's where we compute delta prime. If we compute delta prime using the outer layer solution, compute the formal delta prime that most everybody would use, taking epsilon to 0, it predicts a much broader range of modes than you will see in this Vlasov code. But if you go and look at that inner layer solution over the region where you would want to match, there's actually significant variations in your outer layer equation. So that if you computed your delta prime at some finite offset, delta prime is reduced quite a bit. So the free energy driving the mode that is reduced. So we find that if you just say, okay, I'm going to go ahead and compute delta prime at the thickness of your ion singular layer, it seems to match pretty well. But this is,
That's very interesting. And is there some arbitrariness, therefore, in terms of the result that you get?
well, like, okay, so the thickness of your singular layer, that's the thing on the right, the delta, it's your resonance condition. That we're just using it for the green curve here. And what's setting that for the oblique modes is two things. Your omega there is essentially your drift frequency. It's bigger than your growth rate, so that sets it. Then your shear length for the oblique modes. If we go ahead and write down the shear length on how rapidly K parallel is rotating, that's getting much bigger. So it's those two things.
If you did the matching, say, twice that value or half that value, would you get a substantially different curve?
It would be different. It would be different than this. Yeah.
I think we need to thank Bill again and move on to the next. Oh, does he have?
Yeah, just brief. Your exact Vlasov. Can you get instabilities which are delta prime negative modes due to other sources of free energy?
Yes. I mean that if you put, especially like for the neutral sheet limit, if you put in an anisotropy, either electron or ion temperature anisotropies, you can get modes that make islands. They look like reconnecting modes, right? That are can be strongly unstable.
So they have to look like islands? Other types of things?
Well, of course, there's other modes. There's a broad range of other modes here. Like the lower hybrid drift has a whole big spectrum of complicated modes. Yes, I mean.
So your exact Vlasov gets all this stuff?
That's right, yes. And I'll show it when I talk about, in my other talk, I'm going to talk about the lower hybrid turbulence. And that's one of the same tools we use. It picks up those modes very nicely.
Okay.